So good evening. I'm René Zandbergen, and this is my keynote presentation of the Voynich MS Conference 1922. Sorry, we should start again.
Sure, just starting. I can edit this stuff out.
Yeah.
It's not a problem.
I said 1922, but it was a bit silly.
You're thinking the original one, but anyways.
Yeah. Good evening, I'm René Zandbergen, and this is my keynote presentation of the Voynich Conference 2022. This was originally held in 2022, but this recording has been repeated in October 2024. Any minor changes that have occurred since then will be indicated, but this is nothing very significant. So let's just go ahead. My talk is about transliteration of the Voynich manuscript text. So this is about electronic versions of the text in the Voynich manuscript. This is not about any Voynich manuscript theory. It's about the data that is used in all text analysis of the manuscript. So we will talk about where these data come from, how good these data are, what users should know when using them, and how to best make use of them. Beside this presentation, there's a paper that has already been made available online, and this paper covers the same ground, but this presentation has a slightly different, more practical emphasis. Any differences may be indicated at various points during the talk. This paper also links to a web page with many additional tables and figures. So let's look at the handwritten text. Here we see an image of what this text looks like, and we see writing in lines from left to right in an alphabet that isn't familiar from any other document. So below the picture, we see the symbols, the most frequent symbols used in this handwriting. We can group these characters into different groups. Some look like normal Latin characters here at the top, for example, OA, CI, NMR. Others look like numbers on the second bullet, but others are unfamiliar from other alphabets. Now, the text isn't always written along lines from left to right, but it can also be written along the circumference of circles, as we see here in this figure, or along the radii of these circles, or as what we call labels, so individual words near some illustration, some drawing element. And when it comes to the word transliteration, there's a difference between transcription and transliteration. On the left, we see that transcription is the electronic representation of a handwriting by simply recording the written characters. So we see on the left some handwriting, Aristotelis opera sequentia, and this can be converted to an electronic form. On the right-hand side, we see that transliteration involves actually changing the symbols, so converting symbols from one writing system to another. And this is actually an example of Thai handwriting or Thai writing to the Latin alphabet. Now, the first major transliteration of the Voynich manuscript was done by Friedman and a group, his first study group that he set up in the 1940s. We don't know exactly who were involved in this. We don't have all the names, but they transcribed or transliterated the entire manuscript. However, they omitted text that wasn't standard along writing. So we see in the illustration on the right, this is a copy from Friedman's own copy of the manuscript, where they write punch just this. So only the text in horizontal lines. The individual labels were not recorded. They used capital letters and numbers to represent the text, and we see an example below the figure of what this looked like. This transliteration was discovered only around 1990 in the archives of the Marshall Library in the USA. Now, in the 1970s, there was a second major transliteration effort, which was done by Prescott Currier, shown here in the picture, and he had a lot of help from Merit Imperial. Now, they were unaware of the earlier effort by Friedman et al., and they covered less than half the manuscript. However, their result was published and it has been used extensively by students of the Voynich manuscript. They also used uppercase characters and numbers, and we see above what the FSG transliteration looks like and below what the Courier transliteration looks like. It's similar, but it's different. Now, transliterating this text is complicated. There are several complications because of the character set. So the first one is related to characters that have been called pedestaled gallows. So if we look at the first bullet, we see 5 characters that appear frequently in the text. And then we see combinations of these characters, how they can follow each other. But then we also see that these can be superimposed onto each other. So the characters in red are examples of that. Now, we don't know if these are new characters in their own role or if they are ligatures. And when somebody transliterates this text, he has to make a choice what to do with these. And the FSG transliteration and Courier made different choices. So FSG turned them into 2 symbols and Courier turned them into a single symbol. So they had a different approach for this. Another complication is what we may call strings of I. So there are these little I-shaped characters, and these may precede 4 other symbols. And we see in this little table here how the 4 characters on the left can be preceded by 1 to 3 I shapes. And these are characters of which the ones in light blue appear frequently in the text. And again, how to transliterate these is a matter of choice. And FSG and Courier chose different approaches. So Courier replaced all of these with their own individual character, while FSG only took the ones in red as individual characters, and the others were written out as combinations. There's a third complication, which is that there are all sorts of rare characters in the text that appear only very few times or only once. This is an overview that was made decades ago by Jim Reeds, showing many of these. It's not clear that this list is complete, but this shows that there's another problem to be resolved. Now, in the 1990s, the first person trying to resolve actually these issues was the French linguist Jacques Guy, and he developed a different type of transliteration alphabet, which he called Froggy. And here he split characters into smaller components, which allowed him to address both the pedestal gallows and the strings of I. And in fact, other ligatures that appeared in the last table we saw before. So in the example here, we can see that individual characters may be split into components according to the figure on the left. And then we look at the figure on the right, we see how his transliteration actually mimics the writing quite well. So this is a different approach, and with this he was able to represent the text more completely and more accurately, but there was no major effort to create transliterations using this system. So in the 1990s, Gabriel Landini and myself decided to make a new complete transliteration of the entire manuscript, including all previously missing parts. For this, we knew that we needed a new alphabet to address all the known complications that were mentioned before. So we decided that we wanted to use the principles of Froggy, that is, put things into components, but we did not want to use apostrophes too much, and we did not want to use numbers. We also wanted to match the writing in the manuscript closely, and also decided that we did not want to decide what are individual characters and what are not, because we simply do not know this. We want to represent the shapes in the handwriting by characters in a readable text. So we designed an a priori alphabet, which was designed such that the existing FSG and Courier transliterations could be completely covered by it. So it was a superset of FSG and Courier. And we also took into account the need that we wanted to represent ligatures and rare characters in some way. This a priori alphabet was made almost pronounceable, which caused it to be very easy to learn and easy to use. So this is an overview. We don't need to look at all the symbols here, but on the left, each time we see the actual character in the manuscript. On the right, we see each time the representation by courier, which is always a single character. And in the middle, we see the lowercase character in the Eva representation, which usually, or in many cases, is a single character, but in some cases, for example, near the bottom of the first column, this symbol here has been represented by CH. We have an SH, and we have, in this way, we can represent also the pedestaled gallows in a consistent way, and also the strings of I can be represented in a consistent manner. Now, this was the basic Eva alphabet. Now, during the actual transliteration effort, we knew that we would run into rare characters, and these would all be given a number, which would be a dollar code, a dollar number, semicolon. And we found three types of rare characters. The first one was the new symbols, so single symbols that were not among the known characters. These were all rare. Then we would find ligatures of existing Eva characters. And thirdly, we would find ligatures that also include a new rare symbol. Now, all these new symbols in the first and the third bullet received their own high ASCII code, so in the range 128 to 255. And these codes are represented in transliteration files either as a single high ASCII code, or in order to keep the file completely readable, using the notation at number semicolon. So the full table of these codes after we completed the work covered the codes 132.16 and 242.246 with some gaps. Another important thing is that not all spaces in the manuscript are very clear. There are places where there could be a space, or that maybe there is no space, and these have been encoded with a comma instead of a full stop that was traditionally used for a space between two words. So what does this extended Eva look like? So we see here in the table a case of a rare character, which would have the number 206, or we would have a ligature between curly brackets involving basic Eva characters, or we would have a ligature between brackets involving also a rare character with a high Eva code, high ASCII code. The quote was still used when necessary in rare cases. So here there's a Q character with a quote. It could be part of ligatures. And also frequently in the text, one isn't entirely sure what character we're seeing. Is it an A or is it an O? And then this could be represented by the sequence between brackets, where it means the A is the more likely option, but it might also be an O. So the important aspects of this alphabet is that it's of analytical nature. So it breaks certain things into their components, meaning that certain characters like the Eva CH or the IIN that looks like a cursive M character are perhaps or likely single characters in the manuscript, but they are represented by several symbols. Other characters like this pedestal gallow here might be one or two characters, but is represented by three, and it's not necessarily true that this represents three characters in the meaning of the text. This means that one shouldn't really use Eva transliterations for all types of statistical analyses. It wasn't meant to represent the meaning of the text. It's a representation of what we see in the manuscript. So with the availability of Eva, the Japanese Takeshi Takahashi created a complete transliteration of the manuscript in basic Eva and made this publicly available. At the same time, the work of Landini and myself was not really finished, and we did not yet publish it at this time. And then in parallel, the American Glenn Claston decided that he also wanted to make a complete transliteration, but he could not use Eva for his work. He had his own ideas. So he decided to make a new transliteration based also on the color digital scans that were available in 2004. So similarly to the effort of Landini and myself, he decided to identify new characters as he progressed, and he would use the high ASCII area of the ASCII table for rare characters. His alphabet and his transliteration were made available to all users, but found relatively little use. So by the year 2017, we had 5 different transliterations of the Voynich manuscript text. One of these was not yet published. This was Landini and mine. And the situation was that all of these 5 transliterations use different conventions. They all use different file formats. It wasn't possible to compare them with each other. And the funny situation was that the most detailed and likely most accurate files, namely Claston's V101 and Landini Zandbergen, were hardly used by anyone. So by this time, I decided it was good to introduce a common file format that could represent all, and at the same time publish my own transliteration, so to resolve these issues. Now, without going into too many details, this file format represents 2 things. First of all, it has the data. So it has a transliteration of the text, which is what we see here inside the yellow box. But it also has metadata, which is information about the text. And we see in the next slide here that this metadata, to begin with, we see between brackets F100R. So this marks the start of a new page. It's between brackets. And following that are some page variables, which means this is information about this one page. Then on each line, we get the transliteration of one text item or one locus. And in the red boxes is indicated what type of locus we are seeing here. And this is explained on this slide. So first of all, on the left, we see what these page variables mean. So for example, at the start of a new page, a variable called $L is set to a value which indicates the courier language used on that page, or $H gives the scribal hand as identified by Lisa Davis, or the illustration type, which can be verbal, biological, zodiac, or the quire number, and several others. Now, the locus is identified by 2 characters, the first of which is a capital, and there are 4 possibilities. Either it's normal paragraph text, so basically running text in lines, or it is writing along a circle, or it is radial writing, or it's a label. And for each of these, there are several sub-options, which are indicated by a lowercase character following the capital. So for the labels, for example, we have LA for an astronomical element, LC for a pharmaceutical container, we have full plants, we have stars, zodiac labels, etc., etc. Now, the use of this is that there is, at the same time, a tool which I created, which is called IVTT, that allows a user to process any transliteration using this format. So this tool reads the text, it interprets the metadata, and it can do very different things. It can remove the metadata as one needs. So for text processing, one usually wouldn't want to include it. It can take care of the alternate reading. So when there's an uncertain reading, as indicated before, it can decide to take just the first one. It can also select text based on any combination of page variables and locus types. So there are some examples shown here. If we invoke this tool, IVTT, we can add options. So for example, the first case here shown here is that if we use the option -I, capital H, it means we want to remove all pages that have verbal illustrations. Or if we use +LA, we want to keep only pages with courier A language text. So the first character is the page variable, and the second character is the value of this page variable. In the third example, we see we can combine these. +IZ -C means we keep only zodiac pages, but we remove circular text. This is a very powerful tool. It can do many different things. Any combination of these options is possible. It also uses in a Linux, Unix style, the standard input, the standard output, so it can be combined with other Unix commands in pipes. So this is really for Unix users. And so, for example, this complicated looking command at the bottom of the page takes a complete file, splits it into words, and then sorts these words according to frequency. So in the end, after running this simple command, it takes a complete transliteration file and creates a list of words in decreasing frequency as they appear in the text. And this can be done with any transliteration file that uses this format. So here's an example of using this format and the tools. And we want to check how many hapax legomena there are in a transliteration, or basically in the Voynich manuscript text. And now hapax are words that appear only once in a given text. It is known that the ratio of hapax depends on the number of words and the length of the text. And this is one of the interesting things we want to find out about the Voynich manuscript, to see if it's meaningful, how does it compare with other meaningful texts. So to analyze this for the Voynich manuscript text, I have used the three longest transliterations, the Takahashi, Claston, and my own. And since the last two also indicate spaces that are uncertain, we still have two different options for each, namely to treat the uncertain spaces as spaces or to ignore them. So that gives us 5 different texts, 5 different ways to analyze the hapax. So in the table below, we see for all 5 cases how many words we end up with and how many hapax we end up with in each case. Now, the numbers don't mean too much, so we put them in a graph. And then we see the green symbol is for the Takahashi file. There's only one because it didn't use uncertain spaces. For the blue symbols are based on my own transliteration, and there are 2 cases. The fewer words on the left is for the cases that the uncertain spaces were ignored, and the more words, the larger number of words is for the case where uncertain spaces were treated as spaces. And the same for the GC transliteration, the Claston one in red. And the main takeaway here is that the number can vary anywhere between 14% and 20%. So it's really all over the place, depending on which file one uses and which option of interpreting spaces one uses. So here we see that this statistical result is completely dominated by the accuracy of the transliteration. This is important to keep in mind. Now, to be able to do more, we have all the files in the same format, but we still can't really compare them. I decided to also create a superset of all different transliteration alphabets. So in the past, we had the FSG and Curry alphabets at the bottom of this graph, and these were combined into a superset, basically, which is called the EVA, the basic EVA alphabet. So any text in FSG or Courier can be fully represented in EVA. And then a superset of EVA is the extended EVA with all the rare symbols and ligatures. But at the same level, we have the V101 alphabet by Claston, which has a different way of representing all the rare characters. And the idea is now to combine these two into a single superset called STA, Super Transliteration Alphabet. I will call it STA in the following. Now, extended EVA and V101 both have over 200 different symbols, so the combination of the two will have even more, which means that a single character will not be enough to represent all possible symbols. And in any case, we don't want to use high ASCII. It's very, very inconvenient and old-fashioned. So the way to solve that is to subdivide all characters into families, and each family has similar looking shapes, and the family members are then the different variations of these shapes. So the family names are capital letters from A to Z, and then they're followed by a symbol, which is either the number 1 to 9 if this particular character is deemed to be frequent, or it's a lowercase A to Z for symbols that are rare. Now, to set up this alphabet, several decisions had to be made. Should it be analytical, like Froggy or Eva, or should it be more synthetic, like Courier and V101? It was decided to go for a synthetic approach, which was simply, it's easier. It means it wasn't necessary to decide how to split all the V101 characters into its own components, similar to Eva. And by deciding this, the question of all the pedestal gallows and the possible ligatures of characters was resolved. Each and every single one would get its own code. The second question was about the strings of I, because here we had a bit more variation. So to resolve this, I counted how many characters existed in the extended Eva and V101 file for the various different strings of I characters. Turns out that these counts coincided quite closely, which was good news. And first of all, it appeared that strings that ended in the Eva N symbol or Eva R symbol are quite frequent and can be considered composites, whereas strings ending in the Eva L or Eva M really were not more frequent than other characters preceded by strings of I. So these were considered, these were separated into their components. So as a result, the character that looks like IIR is considered a single character, whereas the character which is Eva IIM is split up into two, II as one and the M, Eva M, as the second. Now this table shows the families, the definition of the families in the star alphabet. I should add here that this is the version of the star alphabet that was the last intermediate version at the time of the original presentation. This has now changed a bit. The definition of the families is the same, but the family codes have been resolved, so that's have been changed. It doesn't really matter. But it shows, for example, there's a family of circle-like characters, O, A, Y, which are the most frequent characters, but they look similar and they behave in a similar way. So they're grouped together. Same with characters that are called crossovers. They have their shape has a crossing line. There's inverted C shapes. Then there are the gallows with a single vertical bar, gallows with two vertical bars, etc., etc. The table goes on. We have different numbers of C shapes. We have the fourth shape, which is special by itself, different numbers of I shapes, and then the various pedestal gallows. And at the end, they're also unclassifiable characters together in one single family. To just show a detail of one family, this was at the time was the J family. Nowadays, this is the M family, but it doesn't really matter. It shows, first of all, the frequent characters or the more frequent characters, J1 through J5, and then some rare characters, JA through JE. This is just an example. The complete star table is really very long. But it shows in the third column how these characters are represented in Eva. In the next column, how these characters are presented in V101. It's completely different. And then it shows also how these characters are represented in the fonts of these transliteration alphabets. Also the counts, how frequently these characters appear. So we see for the frequent characters, this is several tens of times to several hundreds of times. And in the case of the rare characters, it's just a handful of times. A similar table exists, but it's usually longer for all the families. Now, what happens when we use the STA or the star alphabet? So here we see a short line written, short line of writing in the manuscript. This is the fifth line on folio 33 verso. And in the second row of this table, we see how this line appears in the various different transliteration alphabets. It's all quite different, but in the IVDFF format, so the metadata is the same. And now when we translate these 5 lines each into the star alphabet, we get almost identical representations. And in fact, we see there are only 2 characters. There's only 1 character that is different in 2 of the transliterations. Now, it's obvious that this transliteration is really not suitable for human reading. This is really only suitable for automated processing. Now, having this, we can really start to compare all the different transliterations and see how similar or different they are and how complete they are. So when we look at the 5 files, I have designated codes, 2-character codes to each of these files. So FG refers to the FSG file, CD courier, IT is the Takahashi transliteration, the Claston, and Zandbergen Landini. The versions here are old by now. Then the 3rd column shows the number of text loci that are in these files. We can see that the courier file is really much shorter than the others. FSG is quite a lot longer, but the Takahashi, the Claston, and the Zandbergen files are nearly complete. In fact, the last one with 5,389 text items is the complete manuscript text. And we see the number of characters of the complete text is around 157,000 when measured in sta characters. In the following table, I'm comparing each pair of transliteration files. And this is not easy because the files have to be aligned to each other. I mean, they have gaps in different places. But the numbers here in the white boxes show the percentage of common characters. So whenever both files represent a certain character, this is the percentage of cases where this character is identical. And we see the numbers are well over 90. It's only the GC file, which has numbers in the low 90s, whereas the others have numbers in the high 90s. We'll see later why this is the case. Now in light blue, we see the case where the characters may be different, but at least they are in the same family, so the same sta family. And here we see that the correspondence is very high, it's in the high 90s. And in fact, the highest number of all is between Zandbergen and Claston transliterations, which are completely different, completely independent, but at least they coincide most closely. The reason why the Claston transliteration is so different is because it distinguishes between many more different forms of characters that in most other cases, by most other people, were considered one and the same. So creating the sta alphabet was completed in 2020 after numerous iterations. And in fact, there was one iteration after the original presentation. And after making complete comparisons between all the extended Eva and V11 files. This would not have been possible if I hadn't had a tool that converts the text or translates the text from one transliteration alphabet to another. Such a tool existed in the 1990s and was also used when the Eva alphabet was created. And this tool at the time, which is called Bitrans, was developed by Jacques and Pascal, ran in DOS, but the source code is lost. So I created a new version of this tool in C and with the same functionality. I have made very extensive use of this, and basically it uses a table with 2 columns that we see here. And the column on the left represents the list of characters in one alphabet, and the column on the right represents the same characters in another alphabet. And the tool can be instructed to do the transliteration or the translation, I should say, from left to right or from right to left. So that's why it's called Bitrans. It's a bidirectional transliteration tool. This tool can process plain text files, but also recognizes the IVTFF format. And the main way to do that is that it recognizes that certain text should be considered comments or should not be translated. And this is indicated here in this file. So this is a Bitrans input file. We can ignore the top, but say the line here with comment indicates that this tool should ignore anything that is contained between these angular brackets or any line that starts with a hash. It should not translate that. And then it can translate from like left to right or right to left, and it will know in which order it should do this transliteration. It will figure it out by itself. So for example, we see here F1 on the left becomes a C on the right, and G2 becomes CC on the right. But when we translate right to left, it should not translate CC as 2 times F1, but it should knows that it has to convert that to G2. So it figures out the priority of this translation by itself. Now, to convert between the 5 original alphabets or the 4 original alphabets and STA requires quite long tables, but these are all available at my website. And there's information about that also at the additional webpage, which is related to this page, and you can scan the QR code to go there. So besides using ptrans to convert between STA and any of the original alphabets back and forth, it can also be used to create one's own alphabets, or it can be used to convert STA to smaller other approximate alphabets. So for example, files expressed in the STA alphabet can be converted to what I would call nearest basic Eva equivalent. So it takes all the complicated rare forms and converts it to whatever is the most near looking basic Eva character. This is very useful because this is what people will mostly use. Tables that do this are also available at my webpage. Now, of course, such a transliteration, such a conversion creates a loss of information because several different characters may be mapped onto the same, so it's irreversible. However, the tool allows to do that. And everybody can create his own alphabet or character set definition and convert any of the existing transliterations to it. I have used this also to convert text in Eva to alphabets that are more suitable for numerical analysis. And the paper accompanying this talk gives several examples of this. In fact, I had already used something like that, a combination of Eva and Carrier, which I called Kuva, in the year 2000. So this graphic shows how that can be done. If we have on the left any original transliteration, this can be converted to STA. In fact, this has been done. All these files are available at my website. Now then anybody can create a very long table to convert from STA to his own user alphabet, or if he doesn't want to do all that work, he can use the existing table to convert STA to basic Eva and then make his own alphabet and create his own much shorter table from Eva to his own alphabet. We can see how this can be used by looking at the experiment I did before, the analysis of Hapax, where we found that the results were wildly varying for the different alphabets. So I converted the STA alphabet into something simplified. So simplified STA, where essentially I converted all the different shapes that V101, Claston's alphabet, considered different. I converted them to similar shapes. And having done that, I repeated the Hapax counts. So the original points were the open circles that are all over the place. And after having done that, we can see that the new values are the small closed dots. They're very similar for the Takahashi and the Zandbergen transliterations, but they have dropped to more similar values for the GC case. So in this case, after having done that, after having done this alphabet substitution, we see that the variation really only depends on the number of recognized word spaces. So this is just an example of what one can do having a consistent format definition and consistent alphabet definition and tools to process these. I can now show a second example of the use of all these new data and tools. So in or around the year 2000, I analyzed the distribution of character bigrams for each individual page in the Voynich manuscript. So each page became one point in a multidimensional cloud, and this point was color-coded by the type of illustration on the page. So the location in the cloud is a textual property, and the color depends on the illustration. Now, I did this based on my own, not yet published transliteration, similarly to the ZL transliteration used here. I didn't use Eva, but I used the aforementioned Kuva alphabet. At the time, I did not have Bitrans, so the conversion was quite cumbersome, having to use a built-in Unix tool called SED, Stream Editor. And so the cloud was then analyzed using principal component analysis in order to project it on a plane. Now, with all the new tools and data, I repeated this exercise, and the result is shown here. So on the left, the two figures on the left above each other show the original figure based on the unpublished alphabet using the ad hoc tools. On the right, the two plots on the right-hand side of this page are new. They're actually based on the Claston transliteration and using the new format and the new tools. And the two figures are extremely similar to each other. So it is now possible to repeat, after more than 20 years, an analysis using new data, using new formats, and come up with the same result. I mean, this is a very powerful set of tools to process the text. And I can also give an example of how one can define simple ad hoc changes to transliteration alphabets and just see what happens. So on the left, we have first change, which is essentially similar to how I defined the Kuva alphabet. So typically Eva CH is considered a single character, and courier code is a capital S. So we can just do that and just substitute CH by Z, S, substitute SH by Z, and similar changes that coincide with courier's definition and a few other ad hoc changes. It's simply straightforward to just define changes and implement them. Then, after having done this, we can do, so we go from Eva, this is the header line, we go from Eva to something called CUV1, Kuva1. However, after this, we can do a second substitution where we go from Kuva1 to Kuva2. And essentially what this does, among other things, is whenever a character is followed by a small C shape, which is the Eva E character, this is removed. So SE becomes S, ZE becomes Z, and so on and so on. There are many cases where there are 2 or 3 of these in succession, and this simply means that the first one of them is removed. This is not necessarily important, but it's just an example to show the things one can do. So we have the Kuva1 alphabet, which includes some simple changes from basic Eva, and then Kuva2, which has some other arbitrary changes with respect to Kuva1. Now, in the next slide, I show bigram counts. So on the horizontal scale on the left, we have the page number from 1 to 230. This is simply the page, folio 1R, and counting through, leafing through the manuscript until the end. And then we count the number of bigrams, or the percentage of bigrams on the page. So there it's shown in characters on the left. So it's CHO. And we see also the color coding is similar to the earlier figure. So in this case, the red crosses refer to herbal A. So herbal illustrations in the A language. The cyan or light blue is herbal pages in the B language. And we can see how the percentage of this varies across the text and depending on the type of illustration. We can also see how this is for other bigrams, 8, 9, in this case, or dy in Eva, we see that these are really clear indicators of the text or the text properties for each type of illustration running through the manuscript. And some of them are really pronounced. And it took just a couple of minutes to create this plot using the tools. Now, on the right-hand side, we see what happens if we apply also the second transformation, so removing the first E or the first C-shaped character after the other characters. We see that these figures change, and we can use this type of figure to try to come to conclusions about how the text behaves. And this can be done very quickly. These figures were just created in a matter of minutes by simply issuing a few commands, and one can change the character definitions ad hoc and rerun the analysis, create the plots. So I just want to show that this is a very powerful set of tools that is available for everyone to use. So to conclude, we have 5 different and independent transliterations of the Voynich manuscript. They have different levels of completeness and detail, which I have tried to show here. Nowadays, all 5 are available in the same standard format, and there are 2 standard processing tools which are capable of reading this format and performing all sorts of useful transformations on this text. We have also seen that for some types of statistics, the choice of the text and the alphabet used plays an overwhelming role. So one has to be very careful what one is doing. The quality of the transliteration files is different and the completeness is different. But in general, the transliterations are reasonably similar at the order of the 95%. But it means there's a 5% order of magnitude error in each of them. The main uncertainty, in my opinion, is in identifying word spaces. We saw that in the Apex statistics, and this uncertainty in identifying word spaces is likely to play a larger role than is often assumed by many users. We may tentatively conclude that the V101 alphabet may distinguish too many different symbols. We saw how it was quite different when counting the Apex and how this would come down when making it more similar to the other alphabets. However, Eva perhaps has too few different symbols, but we don't really know. Certainly, by converting all transliterations to a single super alphabet, it's becoming trivially easy to use just one or the other file by just changing the input file and running the same analysis tools. And in fact, repeating analysis with different files is one way of checking the reliability of one's results. With the tool called Bitrans, it has also become very easy to just define one's own transliteration alphabet. And one can create one's own transliteration without actually having to transcribe from the images. So, which would take weeks and weeks of continuous work to do that. So one can just do it ad hoc by using any or all of the 5 existing files. And as I have shown, it is also possible to make ad hoc changes to any alphabet quickly and easily, and to analyze the impact of this during any type of text analysis. And that completes my talk for today. And I want to thank you for your attention.